All right, so now we have this vertical mass spring system, right? And so the idea on a vertical mass spring is always try to sketch it out. And it stretches when it's hung and allowed to come to rest. So this mass is 1.25 kilograms. And it's always useful to just have a reference of, if the spring were not stretched, this is the relaxed length, then what we're doing is we're saying, oh, relative to the relaxed length, right now it is stretched a distance of 0.254 meters, 245 meters. Okay, and this is the equal, and then I like to label this position. This is the equilibrium position. Okay, because that's where it's balanced right at the center. The net force is 0 right at that point. What is the spring constant of the vertical spring? Okay, so right now it's not oscillating yet. But, so how are we going to think about it? Well, we know at the equilibrium, we're not going to do energy because there's no, it's just sitting there, right? There's no motion happening. So that's why we're going to just do, it's just statically sitting there. So we know the F net is 0. So we're going to draw a free body diagram. We have gravity. And because we've stretched the spring is trying to get back to its relaxed length. So the spring force is upwards, which is equal to kx. And identify the acceleration. The acceleration is 0 in this system, right? Because it's not accelerating up or down. It's just net force is 0. So therefore we know the forces are equal to each other. And so the spring constant would be mg over x. Now x refers to how much we've stretched the spring from its relaxed length. This is 1.25 times 9.8 divided by 0.245. Okay, so when I get k here, so let's do this. 1.25 times 9.8 divided by 0.245, I get the k is 50. So that's the spring constant there. How much work is required to pull the block down and stretch the spring an additional 0.1 meters? Okay, so we got to think about what is the change in energy of our system. If I do work on it, I got to pull it down. We have to think about what's the change in energy, because work is always the change in energy. That's always the process we think about when we're doing work and energy. Work is the change in energy. Now you could think about the work doing the force times the displacement. However, the force changes because of spring. As I stretch the spring more, it's going to have more force. It requires me to pull harder. So because the force is not constant, I can't do force times distance, right? I have to do the area under it. But it's easier to just think about the change in energy. We think about how much energy is here, and then how much energy is here. So we're going to stretch it to an additional 0.1 meters. So we're going to bring it down to here. An additional 0.1 meters. And let's think about, again, if you don't have any constraint on the system, remember what we always choose is we always choose the system to equal the block plus the earth, because there's a change in height, and then plus the spring when we're doing the work and energy, right? So we're going to include all three things, and then the only work to go from here to here is the work that I do. There's no work done by gravity, there's no work done by the spring force, because they are now internal to the system. So the only work I do is to go from there to there, so we just need to think about what is the change in energy from this point to this point. Okay, so let's call this the initial energy, this point here, and then this point here is the final energy. Now, how much energy do we have? Do we have any kinetic energy at this point? No, because the speed is 0. It's just sitting there. Do we have any gravitational potential energy? Well, if you make this our reference height, h equals 0, we do have some gravitational potential energy, mgh. Do we have any spring potential energy? Yeah, the spring is stretched from its relaxed length, so we have some spring potential energy. So then this is 1.25 times 9.8. What is the height above the h equals 0? 0.1. And how much spring potential energy? K is 50. How much is the spring stretched from its relaxed length from here to here? 0.245. So that would give us how much energy we're going to have at this point. 1.25 times 9.8 times 0.1 plus 0.5 times 50 times 0.245. I need to put that squared. So I'm going to start with 2.73 joules. Okay? Now, how much energy do we have here? Well, down here, when the block is down here, there's no gravitational potential energy. There's no kinetic energy because it's not moving. I've just pulled it down. I'm holding it there. And then we just have spring potential energy, 1/2 kx squared. How much is the spring stretched is the 0.245 plus 0.1. Right, because we've stretched it further. And this is 2.976 joules. And so what's the change in energy? What's the difference in the energy is just the difference of those two numbers. And I get 0.25 joules. That's how much work is being done. All right. After the spring is stretched an additional 0.1 meters, the block is released and undergoes simple harmonic motion. So now it's going to oscillate up and down. And remember, it's going to go up and down. This is the amplitude. It's going to go up and down to the max height, 0.1 meters. So I go ahead and draw that and say this is the max height. Right? Because it's always going to oscillate an equal amplitude up and down around the equilibrium position. What is the period of the oscillation? Period is 2 pi root m over k, which is 2 pi root. What's the mass? 1.25, and then the k is 50. So the period, we just use that formula. And I get 0.99 seconds. What is the amplitude of the oscillations? Amplitude is 0.1 meters. So this is 0.1 meters. What is the maximum speed of the block in the oscillation? So now the energy is a little bit different. Now we have this much energy, right? And we're going to do conservation of energy here. So now back at the equilibrium position, we do have some kinetic energy. Because remember, the max kinetic energy is at the equilibrium position. At the max height and the max stretch positions, we don't have any kinetic energy. But right at the equilibrium, we have the max kinetic energy. There's no kinetic energy there, but max kinetic energy. Now be careful. Not all of the energy here is kinetic energy. So you have to be careful here. We have some kinetic energy. We also have some gravitational potential energy and some spring potential energy because the spring is stretched. So we have all three forms of energy at the equilibrium position, right? So that's 1/2 times 1.25 times v squared plus mg, just this stuff over here, exact same thing. This part hasn't changed because we're still at the same height above our reference height. And the spring is still stretched the same amount from its relaxed length. Okay, so that's that. And then the energy down here is the same because all we have down here is there's no kinetic energy, no gravitational potential energy, only spring potential energy, and that's how much it's stretched. So that's going to equal the 2.976, and then you solve for V. Okay, so it's going to be 2.5 times 2. When I get it, I get 0.63 meters per second. If I did that in the calculator correctly, okay? So that's the idea. We use conservation of energy, we use a period equation, and then sometimes, but you have to draw a very clear picture because there's a lot of stretches. This is what's really important to understand. What does X represent? What do the energies represent? No, in these scenarios, generally it's not going to be 1/2 mv squared equals 1/2 kx squared. You have to think about what is the energy at this point, what is the energy at this point, and set them equal to each other. What forms of energy exist?